Okay, hi everybody. So we are working on intelligent adaptive systems under uncertainty, which was already mentioned here, but different types of uncertainties, both in human interaction with humans and also interaction with the environment, when a robot interacts with the environment. So I'm going to talk about those two projects or research labs. One of them has to do with brain-computer interfaces and specifically self-correcting brain-computer interfaces, which I will elaborate on it for a second. And the other one has to do with robotics and specifically recently we are working on autonomous surgical needle driving using both reinforcement learning and showing how we can do very good synchro, and I'll talk about it at the end. So what is brain-computer interfaces? We put EEG on the scar. We measure the signal through some signal processing, which is very standard. And then the key is a movement classifier, which we are trying to understand what the person is trying to do. So even if when the person is moving the right hand, we know specifically in the brain that there is a location in the small hemispheres in the motor area that should be very active. And it is active when the person is actually moving the hand or when the person is just imagining that he's moving the hand, because there's another center in the brain which decides whether we are going to actually perform the movement or not. So the movement classifier, okay, we're using what is called motor imagery BCI. So the person is just imagining the movement that he wants to do, or the movement that corresponds to the command that he wants to issue. And the movement classifier look at the or get the EEG information and show it later, and then decide what was the intended movement. And send a command to the external device. So for example, if the person the classifier is prone to error because there is a lot of uncertainty about what's going on in the brain. When the person is thinking about moving the hand or even actually moving the hand, he may be thinking about other things at the same time. So there will be a lot of variation for one epoch when he's thinking about going right with the other one. The point is that if the person thinks about moving to the right, but actually the system understood that he wants to go to the left, when the person sees it, it causes some internal error processing in the brain. I mean, error processing is critical for us to learn, to correct what we are doing and to learn new things. So if there is an error, if the system is doing something different than what we intended, there is internal error processing in the brain, which we can detect with the same EEG. It occurs in different areas of the brain. So we can detect those the activity that has to do with the error processing and do what we call self-correcting brain-computer interfaces. So now we have an error classifier that once we give the person the feedback about what we decoded from the movement classifier, we check whether the next 800 milliseconds contain information about that the person processed some errors in the signal, and then use both the information from the error classifier and from the movement classifier to decide how to correct the mistake. So in this strategy, we improve the performance of the system. So I'll show you, I'll show you some experiments that we did, or some prototypes that we developed. The first prototype was to control two animated hands, to close and open two animated hands. So the first step is just the intelligent decoding. Right now we're using a convolutional neural network, but again, some part of the work we are doing in the lab is trying to identify and then develop different types of classifiers to improve the accuracy. There was supposed to be here a very long video that does everything correctly.
The next slide.
Yeah, the next slide has a shorter video which shows the arrow. So here I just explained what's going on. So in order for me to know what the person is gonna do, without me asking all the time, what are you doing? So instead of playing the game, if the color of the ball is green, it's supposed to close. I mean, it's like cold, it's supposed to close the hand. If it's red, it's supposed to open the hand. And if the color doesn't change, then he maintains the pose. So here there's supposed to be a long video showing that everything is checked, but here it's a simple case. It's supposed to open this hand, but it opened by mistake this hand. The system understood that it was an error and closed it. I can show it again. Okay, so it's supposed to open trees, open the system realized there is a mistake. And not only to realize that there is a mistake, to realize what type of mistake, because it could have been that the person was just supposed to maintain the pose. Okay? So just closing the hand that he opened, you realize that it was the wrong hand. So the first part is the intention decoded, and now there was a classifier, the error classifier that says if it's the correct movement and don't do anything, if it's the wrong hand, then close the left hand and open the other one, or just failure to maintain the pose, you should just undo the previous program. And this increased the performance by 10%. This is a very challenging task as well. The post I will get that very proud. I'll tell you in a second what we are still trying to do. Here we are navigating, we're controlling this animated dog. The blue arrow tells the person what he should think or what he should measure. The yellow tells what the system understood. In this case, the system understood not very clear. Let's say that checks why it's not clear. Here it's supposed to go this way. The system understood the other direction. It shows the person that he thought about the other direction, but now we check the arrow, and then the arrow processing, and we correct. Okay, so the first decoding is shown in yellow, and then after we show the yellow sign here, also he thought that he's supposed to go upward, but the system realized that it's an arrow and corrected it a different line. Okay, so we got very good mean accuracy, and we showed that the performance improved by, in this case, by 5%. This has 4 different commands. So when we detect an error, we still have to determine which of the other 3 commands is the right one. And this project is supported by MAPAC and the American DOD, the US DOD. Okay, so what are the current challenges that we're working on? So in general, we're working all the time on trying to improve the classifiers. But so far, I'll just go back to this, so far what I showed you in both cases, there was an error that told the person what to do. The issue of telling the person what to do is not so critical. We tested it, and if the person thinks whatever he wants, it's also okay. What is critical is that we have a clue that tells us when the person starts to imagine. So we know to take the 1 second. Once we give the arrow, we know to take this 1 second, and here is the information. The challenge is to do it asynchronously. So not to show the person any cue, just continuously monitor the EEG and detect when the person has some intention and what is his intention. And this is the work that Eran is doing. He has a poster outside talking about it. And since we're working with GAFAT and we got very good results in the animation, we actually want to do some field experiments with actual dogs. To me, it sounds still very ambitious, but we will try to do some experiments. So I'm looking for people that really want to do some experiments in real world deployment. And now we have a new project, which is funded by the Israeli IAI, רשות החדשנות, Israeli Innovative Center, and with a company that's called BraveSpace. And what we are doing here, we are using the fact that we can detect error-related processing in the brain. And we want to use this information in order to improve the ability of the training system to give feedback to the person. So if the person is doing, in this case, a positive task, he has to press right or left depending on the direction of the middle arrow, and we want him to improve his performance. When the person makes errors, it's very interesting that not only when he observes error, also when person makes errors, there is error-related processing in the brain. It's like sometimes we are doing something and we have a gut feeling that we did it wrong. So if this gut feeling is involved, then we have better error processing in the brain, better error cognition and processing in the brain. And if this signal occurs, then the person can learn by himself. Okay, so if the person detects that he made an error, then there is like a reinforcement signal that he can learn from it. And we can detect whether the person detected his own error, there was an internal error of the cognition or not. And using this information, we can adapt or give feedback to the person. So if there is no error processing in the brain, we want to give when we change the task or give a feedback to the person, so he will then be able to be aware of the error and be able to learn from it. And again, there is many more challenges, and you're welcome to explore them if you're interested. Come talk with me. The other project that I was talking about, okay, so I see that the book is starting to work. So, okay, so what we're trying to do here is that we work with Tomer that has a poster outside. We're trying to go one step beyond what is being done now in teleoperation and do actual autonomous surgery of specific tasks. So it's not like the robot is going to do the whole surgery, but a specific task, and specifically we are aiming at robotic suturing. So we are trying to have a robot that does the suturing, this case specifically the needle driving into the tissue. We're using what's known as stimulus control. I will not go into details about it, but it allows us to do seam to reel very easily. So, and we use reinforcement learning to train actually LSTM to do the task. And so, okay. Okay, so ideally what we want to do is to have the needle going into the tissue without deform. I mean, the tissue will be deformed, but we want the needle to follow the deformation. So this is the trajectory that we want to go. This is a standard PD controller that we see that it didn't follow the trajectory. This is the controller that we developed, which we see that it follows very nicely. And those experiments, again, first experiment is a standard PD controller. You will see that it misses the point that it was supposed to. It gets out like around here. It's very far from the target. And this is the controller that we learned and developed. And it's much closer to the result. So if you want to get more information about this, come to see Tomer's poster or then come and talk to me. So again, we're looking for excellent students, different areas of interest, starting from intelligent system in general, robotics, and software learning, and computer interfaces. Look forward to see you. Bye.